Hello, so for our finals presentation, I'm going to talk about the GeoBoard higher level task that we did towards the beginning of the semester, where we saw how many smaller squares we could fit into a larger square with side length n, and I'm going to talk about the geometric habit of mind I used to solve it. So I'm just going to take a look at the 6x6 larger square that I did. So as you can see, I drew a lot of larger 6x6 squares, and then I started to count and just see how many squares I could fit inside. I started with the upright squares, what I'm calling upright squares, and that just is like a typical square that you would look at. It's not seated at an angle like some of the other ones we're going to look at in a second. And I began with just the largest size it could be, and then went down by 1 unit each time. And as I did this, I noticed a pattern is that the number of squares of that size I could fit started with 1, and then it went up by the squared numbers until I reached a total of n squared for the 1 by 1 upright squares. I also came up with a pattern for how to do what I'm calling tilted squares, these squares that kind of are sat on one corner. How I made sure I was drawing all of these squares is I made up a little counting system, as you can probably see in the corner here. So this 1 by 1 means that I went up 1 and then over 1 to find the next point to connect my diagonal to. You can see it here too, up 1, over 1. And so that gave me a diagonal of side length square root 2 by square root 2. That's just simple Pythagorean theorem. And I continued that pattern to draw all of my tilted squares. As you can see, a 1 by 2 is up 1 over 2. But then a 2 by 1 is slightly different by going up 2 and over 1. So these little counting side lengths that I'm going to call A and B, so A would be up 3 and B would be over 1 in this example, I realized could only sum together to be as large as the side length n. So for example, right here, I could only get up to 3 by 3 because 3 plus 3 equals 6, and anything larger than that I tried wouldn't fit in my 6 by 6 larger square. So I kept track of all my square counts in this table, as well as the side lengths for these are the upright squares. And then there's that A and B again, as well as the little side lengths for the tilted squares. And here's some more tilted square measures. And so I knew it had been easier to draw and find all the kind of upright squares inside the larger square I've been talking about. And like I mentioned, I started with the upright square that was the same size as the larger square with side length n, and then moved down to the total number of 1 by 1 squares that were in the larger square. And that the total number of 1 by 1 little squares was always n squared. So this was obviously the sum of consecutive squares, and so I knew that for upright squares, my total number of squares inside was going to be n times n plus 1 times 2n plus 1 all over 6. The tilted squares, however, were a little bit trickier to figure out. So like I mentioned before, I knew that the side length of these tilted squares was that a squared plus b squared, those little counting lengths I had, and that the sum of a and b couldn't be bigger than the side length of the larger square. So I decided to go to my table and see if I could find a pattern using this information. And I started by looking at a plus b equals 2. So that's just the 1 by 1 counting side, giving me a side length for my tilted squares of root 2 by root 2. And I found that the total number of tilted squares that had side length of root 2, no matter what the n was, gave me t, the total number of tilted squares, was equal to n minus 1 squared. And so I was like, well, okay, let's see if I can find a pattern with this. So I looked at, so that's what we just did. So I looked at a plus b equals 3. So that's my 1 by 2 and 2 by 1 counting side lengths, giving me the tilted square side length of root 5. And I found that t equals 2 times n minus 2 squared. And then for a plus b equals 4, I found that t equals 3 times n minus 3 squared. For a plus b equals 5, I found that t equals 4 times n minus 4 squared. And for a plus b equals 6, and remember that was the biggest one I could get in a 6 by 6 squared, I found that t equals 5 times n minus 5 squared. So I think from here it's pretty easy to see our pattern. When we have, a plus b equal to c, where of course c is less than or equal to n, we have that t, the total number of tilted squares, is c minus 1 times n minus c minus 1 squared. So obviously, again, I need the sum for a plus b equals 2, and a plus b equals 3, a plus b equals 4, all the way up to c. And so I found that that meant that t, the sum of all the t's, was equivalent to n squared times n squared minus 1 all over 12. So then if I was to piece these things together to get the total number of little squares that fit inside the large square of side length n, I had n squared times n squared minus 1 over 12 for the total number of tilted squares. And then I had n times n plus 1 times 2n plus 1 all over 6 for that total number of upright squares I had. Finally, the geometric habit of mind that I really felt that I used in this example was reasoning with relationships. I had to pay close attention to and look for the patterns between certain sizes and orientations of all these different squares. The big one of size n, and then the upright ones, and all the tilted squares inside as well. So that's why I really felt that it was reasoning with relationships. I was looking at those patterns and connections in the relationship between all three of these squares. And so that's all I have. Thank you for watching.